Hi everyone! In the previous chapter, we learned about linear difference equations, and for those we could sometimes find explicit solutions. For nonlinear equations, though, we often have to turn to other kinds of analyses, such as notions of stability. And so that's what we're going to be doing in chapter 2. We're going to be looking at other types of analyses for nonlinear difference equations and systems of difference equations. So let's start with just defining what we mean by an equilibrium solution. So if we start with a first order difference equation, so for the first order difference equation, x sub t plus 1 is equal to some function of x sub t. We're going to talk about what we call an equilibrium solution or a steady state solution. So these mean exactly the same thing. Equilibrium solution or steady state solution. Steady state solution is called is a constant solution x bar to the difference equation. So that's to say, even though this isn't changing with respect to time, we have that x bar is equal to f of x bar. Just as an aside, we can also do this for system of first order linear difference equations. System of, let me just call it a first order system. First order system. And let's write that as x of t is equal to some function, it's called big F of, so that's f of t, x t plus 1 is equal to big F of x of t. Okay, and we call it the same thing. So it's an equilibrium or steady state solution, and it has to satisfy, well, x bar is equal to f of x bar. Okay? And we have the little x bar and big X bar are called fixed points. Fixed points. Because they're things that are fixed under the function f of respectively little f or big F. Let's put that in purple again. Okay, so we're defining what we mean by an equilibrium solution. So these are solutions that remain constant in time. So a lot of the solutions to a difference equation, depending on the initial conditions, will change as time goes on. These are equations that don't change. These are, or sorry, solutions that don't change. They remain fixed under whatever function we're applying. And just for notation's sake, let me be explicit. We're going to let f to the t of some function, of some value f naught, be the repeated application of functions of x naught, where we do this t times. And so then we have if x of t plus 1 is equal to f of x of t, well, then f to the t of x naught is equal to x sub t. Okay. So once we define what we mean by fixed points, we can go ahead and fixed points and steady state solutions. We can also talk about periodic solutions. So equilibrium solutions are the ones that don't change at all. Periodic solutions are the ones that change but then come back to their starting point. So let's make that a little bit more formal. Definition 2.2. So a periodic solution of period m greater than 1. So sometimes you'll see fixed point and like equilibrium solutions also called periodic with period 1. We're not going to do that, but you should be aware of that notation. And so this is a periodic solution of period m greater than 1 of a difference equation x sub t plus 1 is equal to f of x sub t is a real-valued solution x sub k bar satisfying f to the m of xk bar is equal to xk bar. So what we're saying is that after m steps, after m time steps, the solution returns to what it was at step k. And we have that f to the I of xk bar is not equal to xk bar for I equal 1 through m minus 1. So basically, if we were going to say it has a period of m, we actually wanted that to be the smallest possible period. So if it returns earlier, well, then the period is actually something much smaller and not actually a period m. And we'll call a collection of the path that the solution takes an m cycle. M cycle is a set of points. Let's see, x1 bar through xm bar, where f of xk bar is equal to xk plus 1 bar. And for each point, xk bar for k is equal to 1 through m is a periodic solution. Periodic solution of period m. And this makes sense, right? Because if you start with a periodic solution, well, after m step it's going to return to what it started with, and then it's going to repeat every one of those steps again. So each of those other steps is also a periodic solution of period m. Okay, and then we have the set x1 bar, f of x1 bar, and so on, all the way to x of f to the m minus 1 of x1 bar is the periodic orbit. Periodic orbit of x1 bar. These are all just really different ways of saying the same thing. So when you have a periodic solution, things are going to repeat and come back around to the starting point, and they're going to do that over and over and over again. And the periodic orbit of a particular point is just, well, all the points it takes along its path to get back to where it started from. And of course, similar definitions for a first order system. X of t plus 1 is equal to f of x of t. I'm not going to write them out. Basically, periodic solutions, m cycles, and periodic orbits have the same definitions, with the only difference being that instead of everything being a single scalar, there are all these vectors, and you're applying some system of difference equations for the time evolution step. Oh, sorry. Okay, and a couple quick asides. We might go into these. So the first one is that if xk bar is a periodic solution to x sub t plus 1 is equal to f of x sub t, so our difference equation of period m, then xk bar is a fixed point of the function f to the m, and also the function f to the 2m, and f to the 3m, etc. And also, I mentioned this earlier, but I'm just going to write it down. Another aside is that, by definition, a solution of period m can't also be a solution of period k less than m. Can't have period k less than m. Basically, it has to actually take the full m steps to come back around. We'll see some more examples of this in the next lecture that expands on this, but I'm just going to go through and give you the high-level picture here first. So let's continue on with some definitions. This lecture is going to be mostly just lots and lots of definitions because we need to have all the setup before we can prove things in the next couple lectures. So an equilibrium solution x bar of x sub t plus 1 is equal to f of x sub t. Same first order equation many, many times. So we'll call this locally stable. And here we're going to use the delta epsilon definition. If for all epsilon greater than 0, there exists some delta greater than 0, such that if our starting point x naught minus x bar, so the distance between x naught and x bar is less than delta. So if it starts at a distance less than delta, then for xt minus x bar is equal to f of t x naught minus x bar. This distance has to always be less than epsilon for all t greater than or equal to 0. And this, so for any epsilon, you can find a delta such that this is true. And of course, if it's not stable, then we call it unstable. So if x bar is not stable, when it is unstable. Okay, and another related but not equivalent definition, we're going to define what it means to be locally attracting. So again, we have an equilibrium solution, x bar of x sub t plus 1 equal to f of x sub t is locally attracting. Let me move this a bit further up. Is locally attracting if there exists some gamma greater than 0, such that for all x naught, such that x naught minus x bar is less than gamma. So there exists some distance gamma such that if you start out closer to your locally attracting solution, close enough to x bar, well then the limit as time goes to infinity of xt, time goes to infinity of xt, which of course is equal to the limit as time goes to infinity of applying our function ft times of x naught, that is equal to x bar. So if you start close enough, then you always go to whatever the equilibrium solution is, and that means that it's locally attracting. And furthermore, if something is both locally stable and locally attracting, then we have a special term for that. So the equilibrium solution x bar is locally asymptotically stable if it is both attracting and stable. If it is both locally attracting and stable, and locally stable. Let's make that clear. Later on, we'll define what it means to be globally attracting and or stable, but here for today, we're only going to define things locally. Stable. And it's very important to note, and we'll come back to this again in the next lecture, but important. It is possible to be locally attracting but not locally stable, and vice versa. Possible to be locally attracting but not locally stable. And also important, it is possible to be locally stable but not locally attracting. Okay, and I think that finishes all of the definitions. I am going to wait. So if that made sense to you, then great. If not, then in the next video I will be going back through and giving some concrete examples of every one of these definitions and asides. And really just try to give you a little bit better of a sense of the intuition behind all these definitions here. So I will see you in the next video.